than what we took a look at last week. All right, so we're at 14.2. Phase change energy. So the amount of energy that goes into changing a phase. How much energy does it take to melt ice? How much energy does it take to vaporize water? That's what we're going to look at today. The energy involved in phase change. So lots of energy this chapter. This is thermochemistry, unit 14. Thermo is like heat. Heat is energy. So lots of energy. So might as well get started with that. So when we work with energy, which by the way, we symbolize energy as Q. Takes a little while to get used to that. It's kind of weird. I'm not sure exactly why we use Q. I think my guess is it has something to do with the French word for energy. Somebody here take French? You know the French word for energy? I'm guessing it starts with a Q. A lot of the guys, a lot of the chemists that did a lot of the beginnings of thermochemistry were French. So I'm guessing Q is what the French word for energy starts with. So we measure energy, which we symbolize with Q, and the joule, which we symbolize lowercase j. So two new units for you guys to work with there. And then this is important, especially for you guys at home. You watched the lab, you watched my lab video. I didn't do very great in the lab. I did not use enough ice. My ice melted like that, you guys saw. But people in here, you guys did a better job. You used more ice. Didn't just melt like that. You got better data than me. So this is important, especially for those of you at home who watched me do the lab. So really, really important for this chapter, because we will get to temperature changes, but when we're doing a phase change, there is no temperature change. Your substance, now it's often going to be water. We use water a lot, but it doesn't have to be water. In fact, I think in your homework tonight, you guys get a question with aluminum in it, and a question with carbon dioxide in it. So it doesn't have to be water, but we usually use water. The temperature holds steady until all the ice is melted, until that water is gone. And people in class, you guys did a pretty good job of seeing that when you guys gathered data. For those who watched my video, I didn't put enough ice in, it just pretty much immediately started going up. But generally, there is no temperature change until you have changed the phase, until that is complete. So on a graph, water melts, ice melts at 0 degrees Celsius. And it just stays flat until you get water. So from ice to water, there is no temperature change. It's just a flat line. You can add energy. You're increasing the energy, but that temperature does not change until the ice is melted. So again, this chapter, thermochemistry, we're going to be doing a lot of energy calculations. So when we're going through a phase change, the amount of energy that's required to change the phase, like melting or freezing, depends on two things. First of all, the mass. And that one probably makes pretty good sense. You know, an ice cube, a little tiny ice cube you can hold in your hand, it's going to take a lot less energy to melt that than like a whole lake that's frozen over of ice. It's going to take a lot less energy to melt that little tiny ice cube. So the mass, the amount of the object you have present, that's the first thing that it depends how much energy. The second thing is a constant. And that constant is unique to every substance. So water has its own enthalpy of blank, and you insert phase change there. It depends what phase change you're going through. Water has an enthalpy of fusion, and it's such and such a value. Let's go over those in just a minute. Water has a different delta H for vaporizing. It takes a little bit more energy to vaporize water. We'll go over that. Now that delta H is different though, depending on the substance. So if you have carbon dioxide, it has a different enthalpy of fusion, how much energy to freeze it or melt it. So that's what the blank is, whatever phase change it is you're working with, and then whatever substance you have kind of determines what that delta H is. So that's how we calculate the amount of energy with our mass and with our constant. It's really a pretty simple formula. Again, Q, that's energy, is equal to mass times delta H. And again, it's whatever phase change, that blank is whatever phase change you happen to be going through. How much energy to melt something? Well, M times the delta H of fusion. And that's all it is. Not a whole lot to it. For water, again, we'll often work with water. It's a common substance. We all know it. We all know its freezing point. We all know its boiling point, I hope. So it's a really common substance to work with. Now, everything has its own enthalpies of, again, whatever state of matter, but for water, this is a common one. We'll take a look at these. So first up, we have the enthalpy of fusion. Enthalpy of fusion. Why do they use that word instead of just saying melting? I don't know. I wish they would just call it melting, but they don't. So you just have to know that fusion is melting. We just symbolize it, delta H fuse, like that. And that value is 334 joules per gram. So 334, there's that little J, joules per gram of substance. Or, and this is key, or 6.01 kilojoules per mole. Notice the difference in the units there? Watch out for that. Common way to miss points. is you aren't paying attention to your units and use the wrong values. You have to watch your units in this chapter. Have to. You guys know how particular I am and how many points I take off when you don't include units in your work. Well, that's assuming you do the problem right and you just don't put units in. Well, in this chapter, if you don't put units in, there's a good chance you do the problem wrong and use the wrong value. And so not only am I going to take off points for not putting the units in, but I'm also going to take off points because you just didn't do the problem right. So watch that, pay attention to those units. Joules per gram, kilojoules per mole. Kind of know what you're looking at, know what you have to work with, use the right units. Questions so far? All right, well, next one is the enthalpy of solidification, which again is not the word we're looking for. I don't know why they use it. At least this one kind of makes more sense though, solidification. I don't know what the direction is between fusion and melting, but at least solidification makes sense. This one is freezing. So whenever you're going from liquid back to solid, you're going to use your delta H solid. And these values for water, again, keep that in mind. This is only for water. On your homework, when you work with aluminum, I think they give you the delta H solid for aluminum. So you have it there. So the values I'm giving you are only specifically for water. These should look really familiar. Said they should look pretty familiar. Do they look familiar? Well, I hope so. Just wrote them down up here. The only difference really is that negative sign, and we'll talk about that more in just a minute. Questions? Got to turn the page, so good chance you guys to ask questions. Pause for a minute here. Let you guys catch up if you need to. Nothing, we're good? All right. All right, so we've taken a look at our enthalpy of fusion. That's melting, our enthalpy of solidification. Now we have our enthalpy of vaporization. Thank goodness, finally one that uses the same word we use. We symbolize it delta H vape. So how much energy to vaporize a gram of water? And that, again, for water, it's different for different substances, but for water, 2,260 joules per gram. Or 40.7 kilojoules per mole. So again, watch your units. Really important to know what units you have, what units you're working with, and what units you finish with. So you notice that's quite a bit larger than that one we just looked at, right? The first one, the amount of energy to melt water, was only 334 joules per gram. This one, it's like 2,260. It's like 7 times more energy to vaporize the same amount of water as it is to melt. And then the opposite of vaporizing the enthalpy of condensation. Again, that's the reverse process. When you go from gas back to liquid, you condensate. And just like freezing and melting were the same but opposite processes, guess what? Vaporizing and condensing are the same but opposite processes. So kind of a quick note on that. Why are they the same but opposite? They're the same exact process. Going from gas to liquid or liquid to gas, it doesn't really matter. Same exact process, they require the same exact amount of energy. They just happen to have an opposite sign. Because when you're going through condensation, it's an exothermic process. Energy is released to the surrounding world. Now we're thinking, well, wait a minute, if energy is being released, shouldn't that be positive? But no, we're looking at it from the point of view of the water. The water is losing energy. It's being released, so it's a negative value. Whereas vaporization, you have to put energy into it. So it's a positive value. It's an endothermic reaction. So that's where we have the negative and positive signs. So watch out for that this chapter. You can and will have negative energy values. You just got to kind of be aware of that when you do. Questions? Cool. I'm going to work through a couple of quick examples here and then set you guys loose on your homework. So let's take a look here. Our first example, how much energy is absorbed to melt 24.8 grams of ice? Cool. All right, let's figure it out. I like to list out my variables. You guys have seen me do this before. I think it's very helpful. Q, we don't know. Q is energy. I know it's kind of weird, energy, Q, whatever. Q is energy, and that's what they're asking. How much energy? So Q is energy. Mass, well, that's right here. They gave me 24.8 grams of ice. And then delta H. But delta H, what? Is what to stop. Let's read the question, maybe. Let's see. What are they asking for? Absorbed to melt. There we go. Melt. Melt, 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 melt. I was on this page over here. Melting is fusion, and it's 334 joules per gram. So my delta H fuse, 334 joules per gram. All right, so there we go. My formula, there's really only one formula we've learned so far, and so let's use it. Q, my energy is equal to mass times delta H, in this case, fuse. Hey, I've got the unit I want on a side by itself. It's already been isolated. I'm just ready to plug and chug, baby. 24.8 grams times 334 joules per gram. That's going to give me, again, grams will cancel out. I'll be left with just joules, which is my energy. That's what I'm looking for. There we go. Three significant figures. I want 3 in my answer, so 8 to 8. The 3 is not enough to round up. So 8,280 joules. Might sound like a lot, but a joule is a pretty small amount. So even 8,000 of them is not that much heat, not that much energy. There we go. Questions? People at home doing all right? One more example. So how many grams of steam? Steam is water vapor. So steam is water in its gaseous state. Will condense if 2.25 kilojoules of energy is removed. All right, so pretty much same problem, but a little different. I like to list up my variables. Q is energy. They gave me the energy. There's the energy. Now this is key though. If the energy is removed, what sign should I use? Yeah, if that energy is removed, I need a negative sign. We have a negative amount of energy. All right, so there's our energy. Hey, we got energy this time. They're asking for mass. How many grams? Grams is a measurement of mass. So mass, we don't know. We're trying to solve for mass. And delta H, again, we got to figure out which one to use. Let's see here. Condense. We're condensing. We're going from gas back to liquid. So what's my condensate? Well, I've actually got 2 different units here, 2 different values. Which one to use? This gets a little confusing. They're looking for grams, but they gave us kilojoules. So we're looking for grams, but they gave us kilojoules. Guys, you can do either one of these. But there's going to be a conversion for either of them. Whichever one you choose, that's absolutely fine, but you're going to need to make a conversion. If we want to go ahead and use the negative 40.7 kilojoules per mole, guess what? Our answer is going to be in moles. So when you get done, you have to convert it to grams because the question's asking for grams. And that's fine. You can do that. There's nothing wrong with doing that. In fact, most of you guys probably know off the top of your head what the molar mass of water is. You've worked with water for months now. You just did a lab last week where we had the molar mass of water. It's like 18 point something. So that's not hard. You guys can absolutely do that. Just remember, if you use that value, you're ending in moles, and you got to go to grams. Question's asking for grams. I'm going to use the top one, though, because I think it's going to be a little bit easier to convert from kilojoules to joules. Not that going from moles to grams is hard, but this might be just a slight bit easier. We all know, or we all should know by this point, that K in front of something, like KJ, means 1,000. Doesn't matter what that K is in front of. K meter, kilometer, that's 1,000 meters. KG, that's kilogram. It's 1,000 grams. So this is really pretty easy. At negative 2,250 joules. Cool. Now I've got joules. That means now I can use this one here to get to my grams. And my formula, pretty much the only one we've learned so far, energy is equal to mass times the enthalpy. We need to get mass on the side by itself. It's not isolated, but that's not really that difficult, right? We just got to do the opposite of that to get this off the side. It's times delta H condensation. We want to divide both sides by delta H condensation. So Q divided by H con is going to be my math. Now I'm ready to plug in my variables. Oops, I don't want KJ, I want the regular joules. And my joules will cancel out. I've got grams on the bottom. It's like a double negative. It cancels out. Grams on the bottom is the same as grams on top, which is good. I would want grams on top. I want mass. Three significant digits. The 9, the 9, and the 5. The number after the 5 is a 5. That's enough to round up. So 0.9996 grams. My final answer there. So it can melt almost, not melt, we can condense almost 1 gram of steam back into water by removing that much energy. 1 gram is not very much. Like a paper clip is a gram. Pretty small amount. Questions? Comments? Concerns? People online, you all right?